little thing is called a snail ball. It looks like an ordinary ball, but when you put it on a ramp, it does something rather remarkable. It doesn't roll down, it rocks, and then it starts to roll down extremely slowly. So let's make a little mark here where it started off, and I'll tell you a little bit about how it works. So inside the ball you see is a cavity, and the cavity is filled with a viscous sticky liquid like a chocolate, and inside that is another smaller heavy ball bearing. And that means that the centre of mass of the whole system isn't at the centre of this sphere, it's a little bit off-centre. So it doesn't roll down like an ordinary ball would. It goes very slowly, and that's because although gravity is pulling it down the slope, as it does so, the heavy ball is carried back up to the back of the sphere, and that slows it down by giving you a couple in the opposite direction. Then the heavy ball slides down inside, and it's that determines how slowly the ball will move. My colleague Neil Balmforth in Canada did a lovely analysis of this and was able to predict all the behaviour of it. I like to think of using it in committee meetings to limit the time that certain members of committees are allowed to speak when the ball gets to the bottom and at the end of it, however much more they have to say.
So turtles, they like to go forwards and follow each other. They do not like to go backwards. You spin them backwards and they'll go forwards. But you might think it's something to do with this shape that does that. So let me turn them round here. Turn this guy around and turn this guy around. So now they'll go happily forwards, but they do not like to go backwards. This is the original, where it doesn't want to go one way, but it'll happily go the other way. And it's got a slight asymmetry on the shape. But it's crucial there's a bit of friction on the table. If you did it on a completely smooth table, it wouldn't work. And that friction on the table is enough to turn motion like this into a rocking motion, which then gets turned into motion the other way. Because of the slight asymmetry. And this is a very clever one where the shape is actually symmetric, but the turtles facing in opposite directions makes it slightly asymmetric. And that's what's enough to convert a rotating motion to a rocking motion and then back to a rotating motion the other way.
This is a Peppa Pig weeble. It has this very nice peculiar behavior that wherever you start with, it will always end up going up. Now, if you take a random object, a pebble or something like that, you will see that you can start with one side and it will stay there, but if you put it on the other side, it also stays there. But the weeble here is different because it has a single stable position. Of course, there is a trick here, and the trick is that it's weighted at the bottom, and that makes it come back to its position. The mathematical version of this problem is whether there is a shape that we can create or can think of that is homogeneous without the weight, so that it would always go back to the same position. Gabor Domokos and his colleague Peter Varkony in 2006 made the discovery, or invention if you want, of a shape that has exactly these properties. They call it monomonostatic, meaning it has one stable equilibrium point and one unstable equilibrium point. And this is what they call the Gömböc. Wherever you start, you will always end up at this stable configuration. So let's have a look. I start here. Et voilà.